Okay, so welcome to the last lecture of Chemical Principles 2, and in this lecture we are just going to give you some overview of what we learned, essential principles, and also can tell you would like to tell you about some something that's ahead of you. In fact, what we have understood is the fundamental concepts of the principles that govern the chemical changes. However, in practice, when you actually want to see what is happening around you, then you need to have a little bit more knowledge and understanding of how things progress. So, here the purpose of this particular lecture is not for the exam or anything, it is just to tell you that what is ahead and what enormous resources or knowledge that you have right now in your hand to predict what is going to happen given a particular system or observation that is there. You would be able to predict whether things will be things will change or not change. So, let us start with that. So, overview and the road ahead. So, thermodynamics deals with the stability of the system. It tells what should happen, which means that whether it would happen or not, that is a question of chemical kinetics though. Let us say we know that something would happen in a million years from thermodynamics, but we do not know, we will not be able to observe them because it will take a long time. So, what should happen is the thing that thermodynamics tells us. So, we will just review what we have learned, the three laws of thermodynamics, first law, second law and third law. So, first law basically talks about the conservation of energy, that nothing for example, energy cannot be created or destroyed, we know that, right, and that is essentially cast into some kind of forms of energy. So, internal energy, heat and work done. So, it will balance all the time. For example, let us say you are walking on the road and then you are breathing in oxygen, you are breathing out carbon dioxide and you are radiating heat all the time to the environment, and you take carbohydrate, complex carbohydrate that generates the energy in you and also that generates the heat in the body to maintain the temperature and all that, they are perfectly balanced. So, the beginning, and as we discussed before, in the beginning of the universe, whatever the energy content was there, it is still there right now. However, the things are changing and distributing in different way, and that is giving us different forms and shapes. So, you start let us say coal and you burn it, the energy which was stored in that coal is getting distributed everywhere. So, energy is not being destroyed, it is just getting distributed, and by that distribution it is taking different forms and shapes. For example, here you see that oxygen becoming carbon dioxide and things like that, carbohydrate is breaking up and all those possible reactions and happening and all. So, first law is time reversible. So, first law is time reversible. However, we know that there are many processes which are irreversible. For example, if I drop an egg, it will fall down and break it and never come, it will never reassociate by itself and come to my hand. If I drop a pen, it will fall down, it will never come to my hand unless I pick it up. So, we know certain processes are irreversible, yet there is, when you do an energy balance, everything is balanced. So, therefore, first law of thermodynamics lacks in that process of telling what would happen. For example, so let us say there is a hot body and cold body and the energy content let us say is conserved. So, either the heat flows from cold to hot or hot to cold, in either of the cases energy will be conserved. However, we know that only hot to cold, the heat transfers only from hot to cold, high temperature to low temperature spontaneously, and we know that that is not possible, the other one is not possible. Similarly, so we know that perfectly it will be all right if a particular engine takes energy from high temperature and does work. There should not, so it does not violate the first law of thermodynamics because energy is conserved. However, we know that it is not possible. So, second law provides us a direction and tells us that this is okay, this is possible, however, this is not possible and this is also not possible. So, second law of thermodynamics, as we know, tells us that you have, when you take an energy and you do some work, you have to throw out some energy as well, or heat as well, to a low temperature reservoir, and then only it will be possible for the cycle to go on, and it gives us a measure of the efficiency of that engine. And we know that if we do some work on that, then only we can transfer heat from low temperature to high temperature, as we see in refrigerator. So, second law of thermodynamics tells us that efficiency can't be 1 and heat flows spontaneously from high temperature to low temperature. So, second law then gives us a direction. So, it tells us, as we have discussed before, that it gives us the arrow of time. That means, we know that forward in time means entropy of the universe is increasing, backward in time means entropy of the universe will decrease. So, it gives a sense of direction. It will tell what would happen if I drop an egg, it will fall down and break, that would happen. We know that essentially that is a favorable process. So, second law of thermodynamics provides then the spontaneity condition. Spontaneity meaning that what would happen spontaneously. If I do not pick up the pen from the ground, it will remain there. If I drop the pen, it will fall down spontaneously. So, but only to come to my hand, I have to pick up, I have to do some work. So, second law will tell us, or tells us, that what is that spontaneity condition. For example, if I put a drop of ink in water, what will happen? The ink will spread and it will, let us say, fill the whole water. However, the reverse process, it is probable, but extremely extremely improbable for the ink to coagulate and go back. The statistical laws does not say that it is 0. It is just so negligible that it is almost 0. Mathematically it is not 0, but for all practical purposes, the probability of the ink to be coagulated back, we never observe that, because the probability is too small. So, second law tells us that change in the system's entropy plus surroundings entropy, which is equal to universe entropy, has to be greater than 0. So, and since we know that there is nothing beyond the universe or nothing outside of it that can influence the changes in the universe. So, therefore, everything is so everything that we do in the universe is spontaneous, and for that entropy has to increase, which means that entropy of the universe is always increasing, because whatever we do, whether I talk right now or I walk or I sit down, I clean the room and all that, whatever I do, the process is spontaneous as far as the universe is concerned, and therefore, the entropy is increasing. And we know that when the increase will stop, the increase will stop when the system comes to an equilibrium. That means, our universe right now is not an equilibrium. When it will come to equilibrium, then everything will stop. So, all that is, so we also discussed that entropy is nothing but distribution of energy. So, the energy that started in Big Bang with so much concentration at one place, what happened is that it gets distributed with time. So, right now it is still not fully spreaded, right, because we have energy stored in atoms, we have energy stored in coals, we have energy stored in many other places, and let us say sun, we have energy stored in that. So, when all that energy will be equally distributed everywhere, then only the entropy, then only the universe will come to an equilibrium, and that means there will be no organized form available, because any organized form means that the distribution is narrow, distribution is peaked at that place. If I burn a paper, then the energy of the paper gets distributed all across. However, if I do not do that, that paper has now a stored energy, which means it is localized, which means it has that potential to be spreaded out and increase the entropy. So, we know that the beginning was Big Bang, but the end will be a heat death, where there will be nothing left. So, now So, in all spontaneous processes, then total entropy of the universe increases, we know that, and statistically what it means is that the probability that the number of options will increase now for the process to happen, and therefore, it is favorable. And in terms of probability, that the probability distribution has to be more spreaded, as we discussed before. So, spontaneity condition is that delta S universe greater than 0. Now, all that you have to do is that in order to understand whether the process is spontaneous or not, is to calculate system's entropy and surroundings entropy, and therefore, universe entropy, and then we will get an idea about whether the process is spontaneous or not. Now, it is really difficult to calculate the change in entropy of the universe, is not it? But we can always do one thing, we can always look at only at the system and not at the surrounding at all. And if you do that, still there is a way to understand whether the process will be spontaneous or not. So, by just looking at the system, not looking at the surroundings. So, we have discussed before, right, that system's entropy may be lower, but surroundings entropy, if it compensates, then together it will be higher or positive, and therefore, the process will be spontaneous. However, let us say we do not just look at the surrounding at all, we only focus on the system. If we do that, then we can we have to look at some other property. We have discussed that, just I will review a little bit, and that we understand from something called Legendre transformation. So, what is Legendre transformation? So, we know that the fundamental equation of thermodynamics is U is a function of S, V and N. U as a function of S, V and N gives us every information, right. So, Legendre transformation now gives newer fundamental equation. What is that? That H will be a function of S, P and N, A which is Helmholtz free energy, H is enthalpy, A is a function of T, V and N, and G is a function of T, P and N. We have discussed that before. What is Legendre transformation? Why we can write U as a function of S, V and N into G as a function of T, P and N. We have discussed that. So, this is the Gibbs free energy, which by definition is enthalpy minus temperature into entropy. Now, this is something that is the property of the system alone. We can look at the free energy, that is Gibbs free energy of the system, and then we can understand whether this process will be spontaneous or not. So, if I expand, if I differentiate this G, then I can get V dP minus S dt plus mu dN, and for the spontaneous process, the free energy has to be negative. So, that also we have discussed the spontaneity condition, that entropy being positive essentially means delta G being negative, enthalpy being negative, and Helmholtz free energy being negative. So, idea is that why it is that. So, you can understand why it is that, right, because look at here, see if S becomes positive, then minus T S becomes negative, right, and if enthalpy becomes negative, then which means that system's energy is going lower, that lowering of energy or that stabilization releases heat to the environment, and that increases the entropy of the environment. So, essentially it is telling us the same thing, that system plus surroundings entropy is increasing when delta G goes negative. So, therefore, it is the same thing, but we are casting that information by just looking at we are casting this equation to delta G just to look at only the system. Now let us see 4 possible conditions. So, if enthalpy is negative, enthalpy can be positive, entropy can be negative, positive and negative, right. So, let us say enthalpy negative and entropy is positive, then the delta G is spontaneous in all temperatures. Now, let us say enthalpy is positive, but entropy is also positive. So, entropy positive is favorable, enthalpy positive is not favorable. So, that means if the temperature is higher, then this term will become lower. So, it will be a spontaneous process at a higher temperature. So, if you lower down the temperature, then what will happen is that this contribution, this is a favorable contribution now, this favorable contribution will be lesser than this unfavorable contribution. So, therefore, in a lower temperature, therefore, it may not be favorable. So, at a higher temperature, it will be favorable. See, all that we have to do is that say balance between this enthalpy and entropy, and you will see many processes that we see in chemistry, in biology, they are they are either enthalpically favorable, entropically unfavorable, or entropically favorable and enthalpically unfavorable. So, it is called enthalpy entropy balance that always exists. So, now let us look at delta H negative, which is favorable, but and delta S negative, which is unfavorable. And in that case what happens, that since entropy is unfavorable, so it is spontaneous only at a low temperature, because in that case this unfavorable part will be smaller and favorable part will be larger. So, it will be spontaneous only at a low temperature, because at a high temperature what will happen, the entropy contribution will come in and then the process will become unfavorable. And if delta H is positive and delta S is negative, then it is non spontaneous at all temperatures, because delta G will be positive everywhere, because both are unfavorable. So, this is both are favorable, both are unfavorable, here entropically favorable and here enthalpically favorable processes. So, we are going to look at some of the examples now. Let us talk about multi-component system, because we did not cover multi-component system. So, till this you have we have discussed in our normal class, but we have not discussed multi-component system. So, this is your way ahead, that what you are going to learn later. Multi-component or multi-phase, for example, if we talk about water, water is one component system, but then if I talk about water vapor mixture, then that will be two phase one component system. And let us say if I look at water and ethanol mixture, then that will be two component one phase system. So, whether it is a phase or components, ultimately if it is more than one, then there is a chance of transfer of molecules to either different phases, that means a water molecule being in the vapor phase versus in the water phase, that is a transfer of mass to different phases. Or we can talk about two different components, water and ethanol, and there can be a change in the compositions of water and ethanol, and that will give rise to different free energy. And for that what we need is this mu dn part, which we have neglected in our course. We did not really talk about that, because we said that it is one component one phase system. So, n really does not change. If n does not change, then dn contribution dn is 0, and therefore, this mu dn contribution is not required at all. Yeah, mu dn will not be required at all. So, now dg is vdp minus sdt plus mu dn, right. So, now at a constant temperature and pressure, what is going to happen is that dg is nothing but mu dn. Mu is the chemical potential. So, then for one component system, it is nothing but the molar free energy, right, dg by dn. So, for one mole, whatever the free energy is, that is the chemical potential, and you will see it has a great role in understanding the multi-component multi-phase system, in chemical reactions everywhere. Chemical potential plays a very important role, because chemical potentials determine that whether what will be the directions of mass transfer. Just like we know the pressure determines what will be the direction of the volume transfer. If the pressure is high, volume will become lower, if pressure is lower, volume become higher. Similarly, temperature determines the energy transfer. If the temperature is higher, then energy will flow from that high temperature to low. Similarly, if the chemical potential is higher, then the mass will flow from higher chemical potential to lower chemical potential. So, chemical potential is nothing but, you can think of that as a chemical pressure that changes that, right. So, mu is the molar Gibbs free energy for one component system, and if I have multi-component system, then I can write at a constant temperature and pressure dg as mu1 dn1, mu2 dn2 and things like that. So, now let us talk about that in for understanding the solvation. So, increase in entropy results in lowering of chemical potential. For example, when you drop that ink here, then you can show that when the ink gets dissolved, the chemical potential actually reduces, and that reduction in chemical potential actually helps the solution to become stabilized. And of course, if in a dilute limit, one can show that even if the ink does not interact or does not have any enthalpy contribution with the water, it is the entropy. It is the entropy of the process, that the ink is getting distributed all over, that entropy of the process helps to lower down the chemical potential or the free energy of the system. So, delta G is negative in this particular process. So, free energy as you will see is a fine balance between enthalpy and entropy, as we have discussed. So, let us talk about the combustion process, what happens. So, so C2H2 reacting with oxygen will produce CO2 and H2O. Now, if I write down the enthalpy and entropy contribution of this process, then enthalpy is actually a negative number here, minus 1238 kilojoule per mole. Entropy of the process is also negative. So, it is actually entropically unfavorable, enthalpically favorable. Now, when you write the delta G, you see the delta G becomes actually negative for this process. Because the delta G is negative, the process will be spontaneous, even though it is entropically unfavorable. So, why it is happening? Remember, it is not the system entropy, it is systems plus surroundings entropy. Here we are not calculating surroundings entropy, because the surroundings entropy is coming in a way through the enthalpy of the system, which is negative, that is favorable, and it is more favorable than the unfavorable part of coming from entropy. So, it is outweighing or it is balancing the entropic unfavorable part, and therefore, the overall the process is favorable. So, we can say that the reaction is enthalpy driven. So, if enthalpy is the contributing factor for the process to happen, then we will say enthalpy driven. If entropy is the driving factor, then we can call that entropy driven, and if both are favorable, then say it is driven by both. Let us give you some example from very interesting physical phenomena that we see every day around us, and probably we do not understand that in great detail. It is actually it's a research topic till now. So, why oil does not mix with water? Any idea why oil does not mix with water? So, you may think that oil and water does not interact with each other. You may think that they repel each other and things like that, right? But actually water does not hit oil. If you calculate the interaction energy, it is actually favorable, it attracts each other. However, if you look at, let us say, one droplet of water in a microscopic sense, you will see that water molecules are all around this particular oil droplets or oil drop, such that it forms a cage around it. Why it forms a cage around it? Because whenever the oil comes, it cannot form hydrogen bond with it, right, but however, it has a dispersive attractive interaction. Do not think that it has a repulsive interaction, it has an attractive dispersive interaction. This however, it tries to also form hydrogen bond. So, it forms a cage around the oil, form hydrogen bond, but that reduces the entropy of the water, and because it reduces entropy of the water, then when you now again, so that means it is entropically unfavorable process and enthalpically favorable process, but which is more here? Actually the entropy, unfavorable entropy is actually a higher contributing factor here. So, when you add them up together, you will see that. For example, this is a table taken from Widdom's paper, and here the units are in kb, kBT basically. So, you can see that it is there for methane, ethane and propane, and in the butane there the different values are given. I will just draw your attention to methane, to the entropy value and to the enthalpy value. Now, here at 300 Kelvin, that means we have to multiply, we have to take into account of the kBT value at 300, and kBT value at 300 is 0.6 kilocalorie, 0.6 kilocalorie per mole at 300 Kelvin is the value of kBT. Now, let us say we convert that to kilocalorie per mole, enthalpy is minus 3 kilocalorie per mole. So, interaction enthalpy or enthalpy between water and methane is actually minus 3. However, entropy is also negative, and so T delta is, when you calculate, what we get is minus 5.04. So, T delta S contribution is more negative than the negative value of enthalpy, and therefore, the delta G comes to be plus 2.0. So, which means it is an unfavorable process, and therefore, oil and water will not mix. But why it is not mixing? It is not mixing because water entropy gets reduced. So, we can say that oil does not dissolve in water due to the loss in water entropy. Let us now talk about just the opposite process, melting of ice at 20 degrees centigrade. So, we know that it melts, right. Why does it melt? Because if you see that melting of ice to water is actually unfavorable. Why? Because it is breaking the hydrogen bonds. In ice, it has perfectly tetrahedral geometry, where 4 hydrogen bonds are present for all water molecules. Now, if you break it into water, water also has hydrogen bonds, but on an average it has 3.6 hydrogen bonds. So, it is losing 0.4 on an average, by the way. So, it is losing some hydrogen bonds in water. That means, it is enthalpically will not be so favorable, because it is losing hydrogen bond. However, water being liquid, it has much higher entropy, it has translational entropy, it will have rotational entropy, which is not there in ice, because they are fixed, it has vibrational entropy only, but it is losing both translation and rotational entropy. And because of that, you see that when going from ice to water, entropy increases, enthalpy increases, entropy also increases. So, what happens is that at 20 degrees centigrade, I can add that 20 plus 273. So, 20 degrees centigrade, and I calculate that, I get minus 0.44 kilojoule per mole, which means that delta G is negative. Delta G is negative when at 20 degrees centigrade. So, but you see that if I reduce the temperature, what will happen? These negative contributions will be smaller and smaller, and at 0 degree it will be just exactly like the enthalpy, and therefore, at 0 degree centigrade water and ice will be in equilibrium, because their free energies will be equal, and lower than 0 degree, then enthalpy contribution will dominate, and therefore, it will no longer form liquid anymore. So, all that we see is perfect balance of enthalpy and entropy into free energy, and therefore, we know whether the process will be spontaneous or not. We can just have that values and calculate them, and we will be able to understand whether we would one day observe the process or not. Because remember, there is still something called kinetics, which we have not discussed, that tells you that how long the process will take, and that depends on different things, that or mainly that depends on what pathway the process is taking, and in that pathway there will be some point which is the highest in that free energy, that is called transition state, and depending on that the time of that conversion will come. So, but anyway, so we are not discussing about kinetics here, we are discussing about the final points, first equilibrium points and then the final equilibrium points. For example, ice is one equilibrium point, water is another equilibrium point. Whatever happens in between is not the concern of thermodynamics, because thermodynamics goes from one equilibrium state to another equilibrium state. In between we do not observe that, in between you do not see that. If you have to see that, we have to think about kinetics. So, water melts due to gain in water entropy. So, just like that, oil did not dissolve in water due to loss in water entropy, but it melts, and but in this case ice melts to water because gain in water entropy. Okay, so, here some more example of water to ice conversion. So, there is a table taken here where enthalpy, entropy and everything is given, and free energy is also given at 3 different temperature. Minus 10 degrees centigrade, what you see is that delta G of ice is negative and water is positive, and therefore, it will form ice. It does not mean that water will not form at all, but again it is the probability. Minus 51 is a lot to overcome. At 0 degree, however, what happens is that ice and water, as I said, equal in free energy, therefore, they will coexist. At 0 degree ice and water will coexist, because they have the same free energy, and at 10 degree again the water will be lower in free energy and ice will be positive. So, this is the relative value with respect to water is given here, and therefore, at 10 degrees centigrade we will observe water and not ice. Now, let us talk about Gibbs free energy and chemical equilibrium, because in Gibbs free energy also can tell you that how to obtain the free energy when we are talking about a reaction process. For example, A plus B going to C plus D. Now, we know in equilibrium we can write concentration of C multiplied by D divided by concentration of A multiplied by concentration of B. Now, this is an equilibrium constant. Now, this equilibrium constant is again governed by free energy. How? This is governed by this particular equation, that delta G is minus RT ln K equilibrium, which means K equilibrium is e to the power minus delta G by RT. Imagine e to the power minus delta G by RT. If something is more stable, then e to the power of that difference will dictate what will be the the number in that particular sense. For example, if I have C plus D more than A plus B, then K equilibrium will be more than 1. If K equilibrium is more than 1, delta G will be negative. So, process will actually go to the right side. If I have C plus D less than A plus B, then what will happen? Then K equilibrium will be less than 1, and ln of less than 1 is a negative quantity, and therefore, G will be positive. So, if free energy is negative, the process will go forward. If free energy is positive, the process will not go forward. It actually not go forward is not entirely correct. Why? Because it will tell you exactly what will be the probabilities of having C plus D versus A plus B, because K equilibrium will decide that. It will depend on e to the power minus delta G by kBT. It is called the Boltzmann distribution. It is the, so if given two things, one can say that the number of population in this state versus number of population in the other state just depends on their delta G difference. For example, we talked about here this particular point. So, population here versus population here is determined based on the free energy difference between this point and this point. These two will determine the free energy difference, and therefore, the equilibrium constant. So, some of the equilibrium constants are mentioned here, and as you can see that when they are very small, the free energy is highly positive. However, when they are larger, then free energy is more and more negative. So, we will talk about a little bit of binding free energies, and you will see that binding free energies are negative. Therefore, the equilibrium constant is far to the right side. In that case, it will form a favorable binding. So, let us say sometimes the free energies are not favorable. What to do about that? If the free energies are not favorable, one can always couple that reaction with another one where the free energy is favorable, and by that coupling of two processes, one can have an effective or total free energy which is negative, and that will make the process go forward. For example, if I have A plus B which is positive, which means it is not favorable, but C plus D is actually favorable, then you can couple A and C and B and D, and overall free energy, if the delta G, the modulus of delta G is more than the modulus of delta G 1, then the process will be favorable, because the overall contribution overall delta G will be negative. So, let us talk about this particular process, this particular reactions in which the delta G is positive, and then you couple with hydrolysis of ATP, which is minus 30 kilojoule negative, and if you couple these two processes, you actually get minus, it should be minus, just let me write down that one, 16.7 kilojoule per mole. So this happens in the cell all the time, often, and where one not feasible reaction couples with a spontaneous one. So, and that is why in our body ATP is used as a energy currency. So, if let us say there is any reaction that is unfavorable to the extent that unfavorable to the extent of delta G being less than 30 kilojoule per mole. So, if it is unfavorable by more than 30 kilojoule per mole, it will be difficult, but let us say if it is unfavorable by 20 kilojoule per mole, then you can always couple with ATP hydrolysis, and therefore, ATP will be able to supply that energy for the process to happen. So, this is how many non-spontaneous process, which is organized work, that is happening in our body all the time, which is not spontaneous actually, but then the ATP hydrolysis can supply that energy, and therefore, it will be possible. So, actually overall again the delta G is negative, that means inverse entropy is increasing. So, although you see many organized processes like cell growth and things are doing in an organized way, a motor is moving along a particular directions, a cargo is going from one part to another part, looks like extremely organized process, right. But in all those organized processes where the entropy of the universe is going down or free energy is positive, there is an ATP which is supplying the energy, lowering down the overall free energy, and thereby increasing the overall entropy, and it is used as energy currency. one of the most important let me resume. So, there is a very important process in our everyday life for functions of biological molecules, for functions of all biological events, that is called proteins, which are proteins are machineries that do many functions in our body in order for things to happen. And it has to a protein is actually a chain of amino acids, a polymer. There are 20 different amino acids possible, and those 20 different amino acids can have several possible combinations, and that can give several possible proteins. Now, each protein will fold to a particular structure, and because it folds to a particular structure, it does a particular function. Now, it is an important biological molecule, as I said. So, it folds to a particular structure. So, this is a protein. So, if this protein, if it folds in a particular structure, then it is functional. If it does not fold, then it is non-functional. So, for example, and if you see that when it folds, then it will have actually, so if it is, let us say it is a schematic diagram, unfolded state, folded state, and this is also unfolded state and folded state. So, folded state will be lower in free energy. So, that means protein folding is governed by lowering of free energy. So, and because it folds, it does the function, and because it functions, many things actually can happen. And generally it is a new topic altogether. It is a very difficult process, because protein folding is like enthalpically favorable process, because it forms interactions of one amino acid with the other and all that, it make tertiary connections. However, it has to overcome a huge entropic barrier, because there are so many possible ways to combine them, that it has to find the right path from going from unfolded state to the folded state. And how does it do that, still a debatable question, but people believe that it is the mechanism is like a funnel, that if you get into a funnel, you will go down the funnel, right. So, it kind of looks like this kind of funnel. Also, it is a rugged funnel, it is not a smooth funnel, it is kind of a rugged funnel where it finds its way towards the folded state. Again, that is a completely different topic altogether, but as far as thermodynamics is concerned, we researchers including us, we often try to calculate the mechanism of this folding process from this unfolded state. Why? So that given an unknown protein, we should be able to calculate the free energy for the folding of that particular protein. And if we do, then what will happen? What is the advantage? Then given any sequence of amino acids, we will be able to predict the structure. And if we can predict the structure, we will probably be able to predict the function of the protein. And if we do that, then we will understand a lot more about what is going on around us. Another very important thing is drug design. There are pharma industries which try to find new drugs. So, why the drugs are important? So, whenever we have disease or something, we take drugs, right. For example, there is a cancer drug, there is a diabetes drugs, there are drugs for several different things. What they do? Drugs are nothing but molecules. Molecules go and bind to proteins and bind to other places. When they do that, then some kind of signal transaction happens, or some kind of other process happens, and then you feel better, you feel cured. So, people try to find out the target, that where it binds, and once they find the target, they try to find out that what would bind. So, that means they try to find the molecule, and that is a whole new area of research called drug design. There are pharma industries that are trying very hard to find new molecules. You know how much time it takes? It takes almost 12 to 15 years to come up with new molecules, and to make it a drug, even more than that. So, there are not many drugs available, and there are resistance that is coming up from within our body, because bacteria that that can mutate much faster will be resistant towards the common drugs. Therefore, it is very important that we find new drugs. And how do we find that? We find that by knowing the thermodynamics of the process. That means we have to make a molecule which will bind stronger than its competitors. So, let us say there are two proteins that bind, and a bad thing happen. So, then you need one molecule which will bind stronger than the protein-protein interaction, then the protein will not bind anymore, and therefore, you will not have that bad effect coming in, for example cancer. So, this is an example of that. So, a molecule is bound to that. So, one has to find out the free energy of that process. So, many drugs bind to the protein and stop the function, and then binding affinity depends on the free energy, and bound to drug bound state, this D is not bound state is more stable than the drug free state. It is like this kind of free energy profile, where so they are separate, and when they actually bound, the free energy goes lower. Of course, it goes through a barrier process, but that we are not actually discussing. Let us talk about another specific examples. And intercalation of drugs is actually my area of research also. So, what happens is that there are flat molecules which go inside a pair of base pairs of DNA and stops replication of the DNA, and because it stops replication of the DNA, actually it can stop cancer. Why? Because cancer is nothing but uncontrolled growth. Uncontrolled growth comes from replications uncontrollably. So, if you put something to stop that replication, then you will actually prevent cancer or stop the growth. So, intercalation is one of the processes by which it does that. There are drugs like proflavindonomycin which intercalate to the DNA, and this is one of the examples where the drug molecules is actually intercalating by binding first to the minor groove, and then intercalation happens. And then if you see the free energy of the process, then you can see that what happens is that when they are far apart, then let us say the free energy is 0, we can take it to be 0, actually it is not 0, but you can take that as a reference state and 0, and then when it will bind into the minor groove, it will lower the free energy, but then it will have to go through a higher process which is called transition state, but then it will go finally to the intercalated state which is lower than free energy even from the bound and free state, and therefore, you know that ultimately it will intercalate. So, if you choose a molecule that intercalates and gives you lower free energy, then that is the molecule that will prevent the replication process, and that is what people search for. However, in order for a molecule to be drug, binding is not just the criteria. There are many other things one has to look into account. There is called adsorption, distributions, metabolism, excretions. There are many other things one has to. It has to pass through the cell membrane. It cannot get stuck in the lipids. So, therefore, one has to have a proper log p value, some proper partition coefficient and all that. We are not going into detail of that, but one of the major criteria is binding, and that is why there are in big pharma industries there are research and development cells devoted to find out computationally new molecules that would bind to the target better. So, DNA protein binding is similar to drug protein binding, where also there are many processes that the DNA protein binding actually helps do. One is that like transcription process, replication process, DNA repair process and all that, and in all those cases they have the free energy of the process has to be lower, remember, otherwise the process will not happen. So, free energies being lower again means always that entropy of the universe is increasing. It looks like a very organized thing. When you come and clean the room, it looks like you have decreased the entropy, but you have decreased the entropy of the room, not for the universe. You have sweated out your heat to the universe, and that has to be more than the work that you have done to clean it. That is always the process. So, free energy negative is always, it means that entropy of the universe is increasing. That is the beauty of that, and it has to increase all the time, because everything that you do is a spontaneous process, as I said, for the universe, because there is nothing beyond that. So, again DNA protein binding, again, and I am just giving you an example of that how the protein will bind to the DNA. In these steps they are free, and then will come, bind, rotate and go through a barrier, and finally this particular process is called transcription factor proteins, which actually bind and bend the DNA for replication processes, and there it will intercalate into the DNA, and this process has to be free energetically lower. And you see here we are showing the free energy against some coordinate, some reaction coordinate, and you see that finally the final intercalated state for which we can actually get the crystal structure, that is lower in free energy. And this is a computational study done from our group, and actually it is showing you that yes, it is lower in free energy. So, therefore, it will be a spontaneous process. However, to get something in computational way it is difficult, but experimentally if the process happens in milliseconds, seconds and hours and minutes is still doable, but there are some things if it takes let us say an hour, it is somewhat difficult to do in computational way, but yes, there are possible, there are ways to even overcome that kind of situation and understand the process how it happens. So, what is free energy then again? So, free energy is enthalpy minus entropy, right, but then statistically we know that entropy is nothing but options, entropy is nothing but how the probability distribution is distributed. So, it is if you remember we discussed about entropy as S equal to minus Pi ln Pi, right. So, that translates into free energy being something like the ln of the probability distributions multiplied by the RT. So, if something is probable, for example, I will show you here. So, let us say this is a rotation of a simple phenylaniline molecule and this is what the probability distribution looks like. Population, these are the population of two states minus 100. So, these are the dihedral angle. So, minus 100 and this is let us say plus 100. These are the two states where the probabilities are very high. As you see at 0 degree of this dihedral angle, the probability is not there. Now, the probability distribution if that is P, then minus k RT ln P is the free energy, and you see the free energy corresponding to these two states are actually lower, which what it means is that this one and that one are the two stable states, whereas this one is the transition state, which is the least stable state between the two stable states. So, statistically free energy is nothing but the logarithm of the probability distribution, and one can understand that free energy for different processes from different reactions coordinate and from all other things, and thereby one can understand whether the process will happen or not. Okay, so, that brings us to the end of this lecture, and in this I would like to acknowledge a few people and teams that really helped the process to do. So, first is my former student Dr. Raymond Kumar Singh was my PhD student. He has helped me enormously to in many different ways by making demonstrations, looking through the videos and many other ways to complete this process. Then I would like to also acknowledge Vivek Kanadi and his team in Media Center in IISER Pune for all the recording, editing and many other helps whenever required. I would like to thank NPTEL for their excellent conduct of the whole process, and I would like to thank IISER Pune for its support. And thank you all, and best of luck for the exam.